On September 26, 2022, a NASA spacecraft was racing toward a small asteroid at more than 14,000 miles per hour. Its name was DART. And unlike almost every spacecraft ever built, DART was not trying to avoid a collision. It was aiming for one. During the final minutes, its camera transmitted image after image of a world that had never been seen this close before. Dimorphos grew larger. Individual boulders appeared. Then, the surface filled the entire frame. And the signal disappeared. NASA had deliberately crashed a spacecraft into an asteroid. The collision was not an accident. It was an experiment in planetary defense. Every year, astronomers search the sky for asteroids that could one day come dangerously close to Earth. If a large object were found on a collision course with our planet, destroying it might not be the best solution. Instead, even a tiny change in its speed, made years before impact, could cause it to miss Earth completely. NASA wanted to know whether a spacecraft could create that change simply by crashing into an asteroid. Dimorphos was the perfect test target. And, importantly, it was never a threat to Earth. DART began its one-way journey on November 24, 2021. A SpaceX Falcon 9 lifted off from Vandenberg Space Force Base in California. There would be no landing, no sample return, no second mission. The spacecraft had only one purpose: travel through space for more than 10 months, find a tiny asteroid moon, and hit it at exactly the right moment. After separating from the rocket, DART was on its own. More than 6 million miles from Earth, it would eventually have to make the final decisions without waiting for commands from Mission Control. DART was not targeting a giant asteroid. Its destination was Dimorphos, a small moon orbiting the larger asteroid Didymos. Dimorphos is only around 160 meters across. From millions of miles away, it was effectively invisible. During most of the approach, DART could see only Didymos. Then, less than an hour before impact, Dimorphos finally became distinct. At that point, the spacecraft's autonomous navigation system took control. There was simply not enough time for humans on Earth to steer it manually. DART had to recognize the asteroid, distinguish the smaller moon, and guide itself directly into it. As DART closed in, Dimorphos stopped looking like a point of light. It became a world. Its surface was covered with boulders of every size. There were no smooth plains, no obvious crater, just loose rock and debris packed together by weak gravity. The final photographs became sharper every second. For scientists, these images were valuable on their own, but there was no time to study them. DART was moving far too fast. The spacecraft continued transmitting until the surface filled the camera. The final complete image arrived only seconds before impact. At 7:14 p.m. Eastern Time, DART hit Dimorphos. The spacecraft was destroyed instantly. But destruction was the experiment. DART transferred its momentum directly into the asteroid. At the same time, the collision blasted huge amounts of rock and dust away from the surface. That escaping material produced an additional push in the opposite direction. For the first time in history, humans had intentionally changed the motion of a celestial object. But at that moment, NASA still did not know whether the change was large enough to matter.
DART itself could not survive to photograph the aftermath. So NASA had another witness. A small Italian spacecraft called LICIACube had separated from DART before the collision. It flew past the asteroid moments after impact. Its cameras captured enormous streams of debris spreading away from Dimorphos. From millions of miles away, the Hubble Space Telescope also watched the cloud expand. Dimorphos briefly began to resemble a comet. The collision had not simply left a small crater. It had thrown an extraordinary amount of material into space.
Before the collision, Dimorphos completed one orbit around Didymos in about 11 hours and 55 minutes. Astronomers then watched the system for days and measured each new orbit. The result was far larger than the minimum NASA had hoped to detect. Dimorphos was now completing an orbit roughly 32 minutes faster. Its path had changed. DART had worked. Humanity had demonstrated that a spacecraft could intentionally alter the motion of an asteroid, not by destroying it, but by giving it a carefully measured push. As scientists continued studying the data, the story became more complicated. The asteroid did not behave like one solid rock. Dimorphos appears to be a loosely packed rubble pile. The impact changed not only its orbit, but also its shape. And the debris thrown into space played a major role in the deflection. The recoil from that escaping material effectively increased the strength of the impact. In other words, DART's spacecraft provided only part of the push. The asteroid itself amplified the rest. That is important because no two asteroids are built exactly the same way. Years after the collision, scientists were still measuring what DART had changed. And in 2026, they announced something remarkable. The impact had not only changed Dimorphos' orbit around Didymos, it had slightly changed the path of the entire Didymos-Dimorphos system around the Sun. The difference was tiny, only a fraction of a second in a roughly 770-day orbit. But it was measurable. For the first time, a human-made object had measurably altered the path of a celestial body around the Sun. DART was only a test, but if humanity ever discovers an asteroid heading toward Earth, this experiment may become one of the most important missions we ever performed.